Hello, how are you? My name is Peter. I'm a friend of your dad's. He knows my brother Daniel. So I thought I'd help you out with this functions class. I'm tutoring a few people in it. And I'm just going to go over some things just to see what you know. Now, in the links below, you'll see sections that you can skip to. So we're going to look at right now just some basic math concepts. So it'll be division by what you can and cannot do. Division by zero, square rooting negatives, domain and range, how to figure them out, and dividing fractions, things like that. And I'm sure you probably already know a lot of those things, but if you don't, it's good to go over that. Or you can skip to section 2, where we'll go through how to create the inverse function of any function. It's not that hard. It just takes time and practice. We'll more importantly look at parent functions. Now the point of parent functions, and once you learn those, you can create any of the other functions through translation. The reason you learn the parent functions is so that you don't have to calculate out all the other functions. And then we'll probably look at what you're having trouble with, which is translating parent functions and why it's useful to explain this crazy thing that they phrase out, which just makes life complicated in my opinion, which is they phrase it in this way or possibly this way, and it just looks messy and awful. Believe it or not, it's very simple. They just make it hard. And why they phrase it like this in terms of functions is, what this means is the new function, or g of x, is a translation of the parent function or the basic function, and it gets translated in various ways. The a factor affects the y's. It stretches or compresses the y vertically. It's called vertically compression. The k compresses or stretches the horizontal, the x's. And this d simply moves your function left or right along the x-axis, and the c simply moves your function up or down along the y-axis. They've made it complicated with this long thing. It's not. Trust me, it's not. It's also phrased back in the terms of y and x with this, but they still make it look complicated. What they're really concerned about is the k value in this section, because the k is the only slightly complicated thing, and then this can become slightly complicated. But these are very straightforward. And again, don't get intimidated by the phrasing of math. They make it all summarized like this, but you just break it down one at a time, and it's not that hard. But unless you know your parent functions, this is impossible. You must know your parent functions first. So again, anywhere in the video, just simply click on the timestamps down below to jump to areas 1, 2, 3, or 4. Okay, so let's get started. So we're going to go from some basic math. Some basic concepts. Number 1, you can never square root a negative number. That's a rule. That's all there is to it. And the reason we need to know this is because it will dictate the domain and range of some functions. Okay, so you can square root any number that's above 0, including 0. Square root of 0 is 0. But as soon as you enter into -1, -2, any negative number, you cannot do it. It's not allowed. So when you create a negative number in the square root, you're breaking the fundamental rules of math. Another fundamental rule of math is you can never divide a fraction or a number by 0. So 0 can never be in the denominator. So yeah, 1 over 3 is fine. 1 over 0.00001 is even fine, because that's still a number. But as soon as you have just 1 over 0, you cannot divide it. It is breaking the rules of math. So you can never have a 0 at the bottom of a fraction. This will also play a role in the domain of some of the functions. When dividing by a fraction, and you will need to do that in several times in functions, it is a lot easier to learn this. You can just multiply the inverse of the bottom fraction. So let's say I have 2/5 and I need to divide it by 3/6. Okay? Well, that's a pain in the butt to figure out unless you turn this into decimal and this into decimal, but then your calculator is going to spit out a decimal, okay, which it'll spit out 0.8, which isn't useful for you. Instead, you can take this first fraction, so we put that just normally, and you can multiply by the inverse of this one. So that's 3 over 6 down here. So now we're going to multiply by 6 over 3. And it will result in the same answer. I could go into a long explanation as to why is this true, but you can do it multiple examples over and over to see if it's true, and you will always get the same answer. Okay? So let's look at what 2/5 is divided by 3/6. Well, it's the same as 2/5 multiplied by the inverse of this one, 6 over 3. So let's multiply the top. When you multiply fractions, it's very easy. You just multiply the top and you multiply the bottom. And so our top multiplied makes 12. Our bottom multiplied makes 15. Boom. That's the answer, 12 over 15. But the next step is you always must simplify your fractions. 12 can be divided by 3 and 15 can be divided by 3. So when we simplify both these by dividing them by 3, we get 4 over 5, and that's your answer. So we've learned that 2/5 divided by 3/6 is 4 over 5. This will actually be important at some point in functions. Number 4, when figuring out a domain in a square root, we're going to go back to our rule. We cannot have a square root dividing a negative number. So we must find the value of x that will create a 0 or more in the square root function. And that will dictate our domain. If we find an x value that creates a negative, we have gone too far. So let's have a look. X cannot be lower than the value that creates a 0 in the square root. So when we have square root of x minus 3 as one of our functions, what are our limitations in what x can be? Well, x can be any number that creates a 0 or higher. So let's look at the number of x that creates a 0. That's easier to find. Well, if x is 3 in this case, 3 minus 3 creates a 0. So we know that x can be 3. What happens when x is 2? Well, 2 minus 3 creates a negative 1. So we know x cannot be 2. So that means x must be 3 or higher. So we would write the domain as x can be any real number. X can be any real number. But in this case, x must be bigger or equal to 3. And that's not hard to figure out. We just need to figure out what value of x creates a negative number and always be above that. So you can have complicated square roots x's in there, and maybe I'll go into one right now. Look at the top right of the screen. If you have a weird one, like x over 3 plus 3, how do you figure out what x value in this case creates 0? Well, you simply make that equation in the middle equal 0, and then you isolate for x. So first we must get rid of the plus 3 on this side of the equation. So we subtract 3. When we subtract 3 on this side, we must subtract 3 on this side. So we're left with x over 3 is equal to minus 3. Now remember, we're trying to isolate x. So to get rid of this 3 at the bottom, this denominator, we have to multiply by 3 at the numerator, or multiply by its opposite. Well, these cancel out, but anything we do on the left side of the equation, we must do on the right. So we're multiplying by 3, and we're left with x is equal to minus 9. So when x is minus 9, we create a 0 factor. Well, let's test that out. So we'll go back to our original thing. Here we go. If this is instead minus 9, so let's scratch it out and put minus 9, and we divide by that by 3, we're left with minus 3. And minus 3 is plus 3 is 0. So we know that x can be minus 9. Well, which side of the fence do I go on? Is my domain bigger and equal to minus 9 or smaller and equal to that? Well, let's use minus 10 and find out. When x is minus 10, we end up with negative 3.333, or roughly that. And then when we add 3, we're still in the negative zone. we're left with negative 0.33. So we know x cannot be minus 10. Therefore, we must have x's bigger than or equal to minus 9. So minus 8 is fine, minus 7 is fine, minus 6 is fine, minus 5, all the way up to, plus 7, plus 8, infinity, plus infinity. But we cannot go below. We cannot go below minus 10. And so that's how you figure out what your x domain, so that affects your domain. Domain is all x values. It's all horizontal values of your limits for a square root. If you need more help on that, let me know. And finally, 5. Some domains and ranges are automatic depending on the function. So when we're dealing with a line, so we'll call this A. When we're dealing with line functions, so y is equal to x, y is equal to 3x, y is equal to 5/3 x, what, plus 6, doesn't matter what. Whatever creates a line, okay, it'll create a line of some kind or whatever, doesn't matter which way that line is going. That line will have x values that go on forever and y values that go on forever, which means x can be any real number and y can be any real number. So lines have no limitations. There is one exception to that rule. Okay? The exception to that rule is a straight horizontal line in which the x values can be any number, so any real number, because it goes on forever that way. But y is limited by whatever that line is set at. So if that line is set at y is equal to 3, then y is equal to 3. And it cannot go higher and it cannot go lower. It's stuck at 3. And the other exception to that rule is a vertical line. A vertical line, okay? A vertical line's range can be forever. See any y value up and down here. Any y value exists. So y can be anything. But x is limited by wherever that line starts on the Cartesian graph. So if x was over here at 4, then x is limited in its domain by 4. X must equal to 4. So those are the only two exceptions. So lines can go on forever. So automatically, if it's any kind of line with a formula that's like this, you'll know that it's a normal line and its domain is anything and its range is anything. So lines are easy. So are parabolas. So that's the next step to look at over here. Is B an upward or downward parabola? Well, they're easy to figure out. Let's take a downward parabola. The x domains can be anything. X goes on forever and ever in either direction. Easy to figure out. Y is limited by the vertex. So if it's facing downwards, y must be smaller or equal to whatever its y value is for its vertex. Or if it's facing upwards, if we have an upwards parabola, the range is limited by the vertex and the y must be bigger or equal to whatever the y value is over here. And that's obvious because y goes on forever this way, but y doesn't exist this way. So let's say the vertex is 3, 4. The 3 doesn't matter. That's an x value. But the 4 does. So y must be bigger or equal to 4 in this case. Because y's can go on all up here at 5, at 6, at 7. But y does not exist down here at 3 and below. So parabolas are easy to figure out. You just need to figure out the vertex. If you're having trouble with parabolas, let me know. Then we can look at sideways parabolas, and they're limited by two things. So sideways parabola is always going to be in the formula y is equal to the square root of x. And if we look at the basic parent function here, we can see that y goes on forever this way, so above 0. And sorry, I might have drawn it a little crooked on the Cartesian graph here, so I'll make my line straight so it's not too confusing. Okay, boom. So y goes on forever this way, but it does not exist down here. And x goes on forever this way, but it does not exist down here. So we can see that x goes from 0 to positive numbers forever. And y goes from 0 to positive numbers forever. So therefore, x is bigger or equal to 0, and y is bigger or equal to 0. And that makes sense when you look at the formula again. If you look at the formula, y is equal to the square root of x. Well, x can't be a negative number. X cannot be a negative number, so negative 1 is out. Negative 2 is out, negative 3 is out. So that makes sense that x must be bigger or equal to 0. And then if it's bigger and equal to 0, y's result can only be 0 or higher. Because if I put a 0 in there, y is going to be 0. If I put a 4 in there, y is going to be 2. And if I put like a 9 in there, y is going to be a 3. So y can only be bigger or equal to 0. Now obviously this will change depending if it's on this side. We'll see that y will only be in the negative numbers and x will be in the positive numbers still. So y will be smaller or equal to 0 in that case. If the parabola is facing over here, we're now into quadrant 2, and all our x values are negative. So x can only be smaller or equal to 0, whereas y is still bigger or equal to 0 because it's up here. And finally, in the last quadrant, quadrant 3, we'll see that y must be smaller or equal to 0, and x must be smaller or equal to 0, because all the x values are in the negative and all the y values are in the negative. The parabolas can also end up being adjusted upwards and downwards, and that's where it's important to find the starting point, because the starting point will dictate everything that the y values must be and everything that the x values must be. But fortunately, it's very easy to figure out from the formula of the original function. So if I have this, x minus 3, I know that actually this whole thing's going to start at 3. So all my x values must be above 3. And fortunately, all my y values are still simply above 0. I'll show you more of that later if you need. Let's look at the next rule. Absolute values have no limit in domain. They have no limit in their domain, but its range is limited by its vertex. Okay, so most absolute value functions, again, if you need help on these, let me know, are like that. That's the parent function. So we can see that, well, x's go on forever. X's go on forever. So that's x's domain just means x is any real number. But y is limited by its vertex. It's here. In this case, it's 0, 0. So there's my y value. And upwards. So y must be bigger or equal to 0. Again, that's going to change because you can have translated absolute values that start here. Let's say it's that vertex. Let's say it's 0, minus 3. So I know my y value is minus 3 and upwards, so y must be bigger or equal to minus 3. So just finding the vertex is important. And again, that will be revealed in the formula. You can also have them facing downwards, in which case your y's will always be smaller or equal to whatever the vertex value is. Again, we can go into more detail if you want. And finally, a 1x function, 1 over x function, is interesting. Y is equal to 1 over x. And it looks like this. And I'll try to do a normal Cartesian graph first. A bit crooked, but that's okay. And I'll do the graph itself in red. It looks like it looks like this. Something interesting happens to that. It turns out it can have all y positive values. It can have all y negative values. It can have all x positive values. And it can have all x negative values, but there's one rule it has to follow. These graphs always approach but never touch the x and y axes. So x can never be 0 and y can never be 0. They get close, forever and ever they get close, but they never reach the x or y axes. So that means their domain and range is going to be dictated by these lines called the asymptotes. Asymptotes are lines that they approach but never reach. So in a parent 1 over x function, x and y can be any real number with one exception. X cannot be 0, y cannot be 0. And that's because it follows the basic math rule. We cannot have a 0 down here at the bottom denominator of a fraction. As such, x must always be smaller than 0 or always be bigger than 0, which means the resulting fraction will always be bigger than 0 or always be smaller than 0. Because no matter how small I make x, if I make x 0.000001, this number will become like 1 million. If I make x value 1 million down here, this fraction will result in 0.00001, but it'll still never reach 0. So that stems from the fact that you can never have 0 as the denominator of a fraction. There's some basic math concepts that you need to understand for functions. Let's go to the next section, slide 2. These are the parent functions. These are the only functions that you should essentially memorize where they start and some of their basic numbers. Now on the left, it's also very important that you understand these 4 quadrants, and I'm sure you probably already do. So quadrant 1 only has positive x values and only has positive y values. Anything in this area, the x's will always be plus and the y's will always be plus. That's quadrant 1. In quadrant 2, the x values are always negative, but the y values are always positive. Makes sense. We're up here on the y-axis, but we're over on the left side on the x-axis. So it's important to know that if any function is in there, the x values will be negative and the y values will be positive. Quadrant 3 is the area where all x's are negative, all y's are negative as well. Makes sense. This is on the left side of the x values and the downside of the y values. And finally, quadrant 4. We're dealing with only positive x's but negative y's. And they number them like that. 1, 2, 3, 4. And this will be important in future math as well, because in circles, this is how it'll be dealt with as well for angles and things. So it's important you understand your quadrants. Second, this y-axis is often referred to as the vertical axis. Vertical. And that makes sense. Vertical is up and down. And then this x-axis is referred to as the horizontal axis. And that makes sense because it's like the horizon. So this is important because we'll be talking later about stretches and compressions. And they'll also be often be called horizontal stretches and compressions, or vertical stretches and compressions. Forgive my writing. And that is why I want you to be familiar with that. Now let's look at the easiest one to understand, the parabola. The formula for parabola, the standard parent function. A parent function is the basic root, simplest to understand function. And we'll be translating all of these. So the parent function is y is equal to x squared, and you should understand these values. When x is minus 3, we plug it into the equation, it gets squared, and it becomes y is 9. And it becomes positive always because any negative squared will become positive. Same with negative 2 squared becomes 4. Negative 1 becomes 1. So that's why we have these points over here. One's off the graph. There's 2, 4. There's 1, 1. That's negative 2, 4, by the way. Negative 2, 4. And that's why you should know where they're plotted on the graph. And this is important later on in translations. And then as we enter into the 0, 0 squared is 0. 1 squared is 1. 2 squared is 4. And 3 squared is 9. Now notice that the y values repeat. The y values repeat again. That's because the square root, or the square of these numbers, will result in the same positive y values. That's important to note as well. And it also explains why, if I take a line and draw it across my parabola, I will find two different y, or the same y values here. Let's say that's 4 and 4, but opposite negative x values. And this is called symmetry. Symmetry. And it's symmetrical right now along through the y-axis. Okay? Y-axis. So it's kind of like the y-axis is a mirror, and everything here gets reflected on the other side. That's an important concept to understand, reflection. So that means everything that happens here will happen here, so it'll have the same y value, but opposite x values, so -2 here and +2 x values there. Okay? So that's good to know, because that means if I know my one side of my parabola, I can simply graph the other side reflecting it in the y-axis. Very handy to know, and a very important part of functions. So really you only need to know one side of your parabola to draw the other side. It's also going to be important in how we translate a parabola up or down, right or left, and how we stretch it or compress it, or stretch it horizontally, or compress it horizontally. Now, we'll get more into that later. It's important, though, that you memorize these values, and they're pretty straightforward. Let's go on to the next one, and I failed to write the formula for it, but it's y is equal to the square root of x. And it's interesting, you would think it would produce both values, like it would just be this sideways, but it doesn't. That is because we cannot have a negative number in the x values. So when I plug in my negative x values, I get an error on my calculator, which means y can never be negative either in the parent function. So we're limited. Our domain must be x is bigger or equal to 0, which in turn makes our y bigger or equal to 0 as well. So we can see right away we have a parent function that has a limitation on its domain and range. And the basic numbers right away are this. And by the way, I skip up on my x values just to make the square root easier. Since these are pure square roots, they're easier to see on our graph. So the square root of 0 is, of course, 0. The square root of 1 is, of course, 1. The square root of x value of 4 makes y value 2. And the square root of 9 is 3. Square root of 16 is 4. Square root of 25 is 5. These are my basic numbers, and I should know how to plot them on my graph. There's 0, 0, 0, 0 there. There's 1, 1 there. And there's 4, 2 there. And then the rest go off the graph. But it'll really help me to know these numbers when I do translations of functions, which really is what the next couple chapters is all about. So this function is y is equal to the square root of x. Then we come over to this function. These are the 4 basic functions we're doing, by the way, and its formula is right here. Y is equal to the absolute value of x, which means whatever value of x we take in here, we're going to make it positive no matter what it is, and that positive value will become y. And actually, this thing is like a line, even though you can't see it. If this was a line, if it was just y is equal to x, it would go on forever down here, right? The green thing is the line. It would be a line called y is equal to x. But as soon as we slap that that absolute value in, all this line jumps up to positive y and becomes this red line. So really, y is equal to absolute value of x shares a lot in common with a line. And as you can see, no matter what value of x we get the same value of y, but in the positive. So minus 2x becomes positive 2. Minus 1x becomes positive 1y. 0 is simply 0. And 1 becomes 1, 2 becomes 2. So this side is very much like a line. We can see the values are the same as a line. It's this area where the negative x's become positive y's that changes everything. And our domain is, as mentioned, our domain x values can go on forever in any direction. But our y values, our range, our y values is dictated by the vertex. Now the vertex of this one is 0, 0, just as, by the way, up here is 0, 0, and up here is 0, 0. They all have 0, 0 standard vertexes. So because this standard one is a 0, 0 vertex, but its y values are only ever positive, that means y for the range must be bigger or equal to 0. This can change when we translate this absolute value. You can translate an absolute value downwards. You can translate an absolute value downwards and to the left. But its range will always be dictated by its vertex and up. And in some cases, you can make one that faces down, in which case the range will be dictated by its vertex and downwards. But the x values will always go on forever this way. Same with this parabola up here. The x values always go on forever this way. Only this one is limited. Now let's move on to our next function, which I also did not write it down, but our next function here is y is equal to 1 over x. And I've put the values over here in fraction format so that it's easier to understand the points on the graph. Y is always simply going to be a flip of x. So whatever x is, if it's in fraction form, you just flip it upside down. And if it's number form, you put it in fraction form. So let's have a look at this, what it looks like on the graph. You have this interesting line here, which is in quadrant 1, and this interesting line here, which is in quadrant 3. Now remember that in quadrant 3, all x values are negative, all y values are negative. In quadrant 1, all x values and all y values are positive. And the interesting thing is x can be any number either way with one exception, and y can be any number either way with one exception, and the exception is called the asymptotes. The green lines represent, in this case, the asymptotes. The graph of this function approaches the axes but never reaches it. And again, this comes to our rule of math. Because x can never be a 0 at the bottom of a fraction, we will never get a 0x value. And as a result, because x is never 0, we will never get a y that's 0, because there's no way this fraction can ever become 0. So therefore, we have an interesting sketch where the domain is x is any real number with one exception, x cannot be 0, and y can be any real number with one exception, y cannot be 0. And the basic points to graph and to remember are fairly easy to remember, actually, and here they are over here. Let's see if I can get rid of some of this stuff. Okay. And yeah, they're over here. If x is minus 1 over 3, y is minus 3. If x is minus 1 over 2, y is minus 2. I simply flip this fraction upside down. If x is minus 1, y is minus 1. And that's where we see the one easy to plot point right here. And then we can't have any zeros, so that's why there's no zeros here. But you can have a minus 2, and y becomes minus 1 over 2. Now entering into the positive zone, well, there's no 0, 0 for a reason, but you can have a crazy fraction too, like 1 over a million. And what do you think 1 over a million fraction would create in the y value? It would create 1 million y, simply the flip. So you can see that as x gets really small, y gets really big. As x gets really big, y gets really small, and that's the rule with this. So see, as x gets really big, y gets really small. As x gets really small, y here gets really big. And that's true in the negative zone. As x gets to be a smaller and smaller number, y technically approaches 0. And when I say smaller, it's because it's becoming a bigger negative number. I'll use that phrasing. As it becomes a bigger negative number, y becomes a much smaller negative number. As x becomes a much smaller negative number, y becomes a much bigger negative number. So they're always opposites, exact opposites actually, unless we apply some translations. Now, the asymptotes can change. The asymptotes can change. That's because, again, we can translate these graphs later on, and they can end up moving. But again, they will always have an asymptote that they never reach, and we can figure that out based on whatever the fraction is. So, for instance, if y gets translated to 1 over x minus 1, well, remember, we can't have a 0 down here. So that means x can't be 1 here. X can't be 1. And since x can't be 1, its asymptote would become right here. Its asymptote would, that's a terrible drawing, but its asymptote would essentially be x cannot be 1. And so the whole graph would shift that way. It would be drawn around the x is equal to 1. And as a result, when x can't be equal to 1, y won't be equal to 1 either. But again, I'll show you how to figure that out. Okay? So these are the basic parent graphs, and you need to graph several things about them. You need to know which one is what. So this is y is equal to 1 over x. This is y is equal to absolute x. This is y is equal to the square root of x. And this is y is equal to x squared. And you need to know their basic numbers. And that is because when we translate them, we're not going to regraph everything over and over again. We're simply going to take these numbers and learn how to translate them. And finally, we're coming to the section that you probably are the one you're puzzled over. So you've probably skipped to this one. And that is the transformations of these parent graphs. Now, they've made it endlessly complicated by phrasing it in these crazy formulas that are just, ugh. And you go, oh my God, I'm not going to figure this out, and I'm not sure I want to. And I don't blame you, because look, what the hell, why is this g of x there, and then this an f, why is the a in front of the f, and what's this k doing here? Ah, God. And then they even try to simplify it for you, and it still looks like a mess. So, or y is equal to a f k x, y still, God almighty. But the reality is the only numbers you need to focus on are the a, the k, the d, and the c. And those are simple rules. And guess what? The c and the a are crazy simple. So you're going to learn the a and the c easily. But what your textbook is focusing right now on is the k, because the k gets a little confusing in how to interpret it. And as a result, if there's also a reflection, the d gets slightly confusing. And so that is why I really want you to learn this. I want you to have this formula. It's a website that helps you easily translate all the parent functions. And you'll see here that I've put all the parent functions up already. Yuck. But we can look at them one at a time. Here's a parabola. And here's the parent, y is equal to square root of x. And here's the absolute value, y is equal to the absolute value of x. And here's y is equal to 1 over x. And the beautiful thing about this website is if we alter the formula, we can see visually, so I've added +2 at the end, we can see visually what happens. That +2 that I have added at the end is actually a c value. So I've added a c value there. Okay? And this is a great website to understand the translations. I'm adding an a value in front of this. It would have been easier if I put a bracket in front of the x to make it all clear. So I'm adding an a value in front. I messed that up. Let's see if it'll let me do it like that. No, it didn't. Square root of 2. And what happens if I put a 3 in front of it? Well, it got skinnier. The 3 created what's called a stretch. We're going to get into that. What if I put 1 over a fraction in front of it? 1/2. Well, I fattened it up. I created what's called a vertical compression. So we're going to see that more. And guess what? If you do that same thing to the other graphs, if I put an a value in front of this square root of x, it's going to create a vertical stretch. And if I put a fraction in front of it, it's going to create a vertical compression. It compressed it downwards. Don't worry about that yet. I just wanted to show you this website because it's a beautiful way of punching these in and visualizing what happens to these graphs if I add numbers. So see, I'm adding a value to the end. I'm adding an a value. I think a was the term, right? No, c value. And the whole graph went upwards by 6. And the new asymptotes became y is equal to 6 and x is equal to 0 because all that happened was y got changed by 6. But again, don't worry about that. We're going to get into instead what these numbers mean and why are they in there and how do I figure them out. So let's look at that. We're going to look at that by taking our parent functions again. So let's take one of our parent functions. We're going to take, don't save, we're going to take, I opened the wrong one. Let's take our favorite one, the parabola. So I'm going to take a parabola. And we're going to look at it if I change it in various ways. All right? So remember that I said that they made it needlessly complicated by putting an a f of x minus d here, and they put a k in front of the x, and then they added did I get my d and c wrong? I can't remember actually, but it doesn't matter. They made it endlessly complicated. So let's instead look at what those numbers are. Yeah, the d's in the middle, c's at the end. So let's instead look at it like this. We know our parabola is like that. Y is equal to x squared. And we can change it in one of four ways that they've described to us. A, which will affect vertical and compressions or stretches. A. And we're going to get into it, so don't worry about memorizing that yet. We can look at k values, which would go in front of the x before it's squared. And this is an important thing to distinguish. The k is beside the x before something happens to it, before it gets squared or square rooted or whatever. So that's how you distinguish the k from the a. So both of them affect the stretching horizontally of the graph. And again, don't worry about it just yet. The minus d here inside with the x, so that's how you notice it. The minus the d, the reason they put minus here is it's really a bit, they're just saying don't forget to do the opposite, and we'll get into that. But let's say it said x plus 3. You would think, okay, well, the entire graph is going to shift right by plus 3. So my new parabola is going to be somewhere over here, like this, and its vertex is going to be over here at the 3. But this is one of the tricky rules, those tricky rules. Plus 3 with the x actually has the opposite effect, and we're going to see why in a bit. And it actually moves the whole parabola 3 to the left. So my vertex goes from 0, 0, and it moves the x value minus 3, 0. So we're going to get over that, into that, and why that happens. But whatever's here, it actually translates the parabola the opposite. And again, there's another exception to that. So it translates the opposite. Any values that we have on the end, also known as the c value. So what I'll do is I'll put this up here so we have it the whole time. And I'll do it like this and make it all slightly messy again. And I'll crop it, and then I'll just get rid of some of the stuff. Get rid of that, get rid of that. And we'll just we'll keep this up here, okay? So let's look at some things. Let's take our original parabola. Y is equal to x squared. Here's the values. And let's simply add 3 and at the end of it. And it's outside of the x, so it's not inside a bracket. The difference, if it was d, you'd see this. You'd see, let's see if I can get rid of that. You'd see a bracket x plus 3 squared. That's when you'd know we're dealing with a d. But I'm saying, no, I want to look at my c's. My c's are my easiest things to figure out. So x squared plus 4, let's say, plus 3. What will happen? Well, it's easy to figure out that once after we figured out a calculation for x, we're simply going to add 3 to it. Or in other words, y will change by plus 3. That means if I have this formula, y is equal to x squared plus 3, I simply take my original value of parabola and it's going to shift up the y axis 3. So it's going to start here, right here at 0, 3. And if I look at my table of content, or my table of values here, it simply means I add 3 to each value of y to figure out my new plot points if I needed to. So let's have a look at that. Okay, and we're going to use the Desmos calculator to see what values we get to make sure we got it right. So y is equal to x squared plus 3 means, oh, I'm just going to add 3 to each y value to get my new y value. So 9 plus 3 is 12, badly written 12. 4 plus 3 becomes 7. 1 plus 3 becomes 4. 0 plus 3 becomes 3, which is why my new vertex is there. 1 plus 3 becomes 4. 4 plus 3 becomes 7, and 9 plus 3 becomes 12. And again, notice I've done it right because I have these matching y values again. And nothing happened to the x values. They stayed the same. That's because in here, there was no alteration to the parent x function. So x didn't get anything added or multiplied to it. So I can just not worry about x. I just worry about what happened to y. Well, y increased everything by 3. And that just means that my new graph has gone up by 3. Oh, badly drawn. It wasn't greatly drawn before anyway. And there's my new vertex, and my new domain is y is bigger or equal to 3. And that was easy to figure out because a vertex, as you remember in any parabola, the vertex is right in the parabola. So in this case, if this is the parabola, and I hope you know this much. If you don't, we'll have to talk. But the vertex is right in the formula there. The vertex is actually the opposite x, so plus 2, comma, whatever this is, plus 3. So that's my vertex, which means if it's an upward facing parabola, my vertex range is dictated by that number, and y must be bigger or equal to 3. It's important that you understand vertex notation. If you don't, we have to talk. Okay, so that's great. That was easy to figure out. All my y values got altered by 3. That's simple. Let's look at when I multiply it by 3. So again, I have the 3, and then I have my x in a bracket and squared. And I'm like, well, how can I tell if that's k or a? Well, if it was a k, it would have been written like this. Instead of 3 outside, it would have been written brackets 3x and then squared. And that is a k because it gets applied to the x before it gets squared. You also might see it sometimes like this, x minus 3, and then they'll put a square bracket here and have a 4 out here. This 4 would be the a, this 3 would be the k, but it's usually right beside the x. So you're more often going to see it like this, 3x plus whatever if there's anything in there, but you might just see 3x squared. When it's right beside the x like that in the bracket, we know we're dealing with a k. We're not going to do the k's yet. We're looking for an a, so it's going to be 3 and then the bracket x and then squared. And I know it's an a because it's not in the bracket. So that means I'm going to simply be affecting all my y values. So all my x values are going to be the same again. All my x values are going to be the same again. They don't change. I square them first, and then I simply multiply them by 3. Or I can just look at all my y values and multiply them by 3. So I'm going to multiply them by 3. So this becomes 27. This one becomes 12. This one becomes 3. This one stays at 0. Notice my vertex didn't change when I multiplied it by 3. And then the same numbers appear on the other side, 3, 12, and 27. All my y values simply got multiplied by 3. And that's why I say the easiest ones to figure out are the c and the a. Because c will either just shift the whole thing up or down, and a will stretch it or fatten it depending on what the a value is. And we'll get into that too. Let's see if that's true using Desmos. Let's throw a couple of these graphs up there and see what this happens. And by the way, if I was to graph it, I would simply now use my new points of 12, 3. So this here is no longer this one. And it's too bad this I left this graph up, but I'll just try to erase it here. And there, like that. And all my 3 values, what used to be minus 3 comma 9 is now minus 3 comma 27, so it's way off the chart. And my minus 2 4 became minus 2 12, so it's also off this particular chart. But my minus 1 1 became minus 1 3, which is on the chart. It would be somewhere up here, right here. So we can see my entire graph kind of got thinner. And this is called a vertical stretch. A vertical stretch. And It's called a vertical stretch by a factor of 3. And it's the same number in here as out. And it's easy to figure out. Now, if the number in front, a, is bigger than 1, it will always create a stretch. When the number is a half, what happens? What happens when it's a half? Well, or smaller than 1, smaller than 1. Well, let's take a half. Y is equal to a half, and then bracket x squared. So again, we know this is an a value because it's outside the bracket. And I simply take all my y values and multiply them by a half, or half them. So 9 becomes 4.5, 4 becomes 2, 1 becomes a half, and the same on the other side, 2 and 4.5. So if I were to plot this, I can see that it's still the same vertex. It becomes 1 and a half, so it's here. 2 and, it became 2 and 2, which is here. It became 3 and 4.5, which is about here. And the same thing on the other side. So I can just mirror it instead of figuring it out. And in this case, my parabola got fatter. It got fatter. So in the y values, it got squished or compressed. By squishing all my y values down by a factor of a half, I compressed the entire parabola and I made it fatter. Let's go to Desmos and see if that's true. Let's go to, we're going to take parabola because it's easy to work with. And I'm going to put 3 parabolas up there. I'm going to copy the parabola formula. And I'm going to put it down there. And another one down there. And I'm going to put a 3 in front of this one. And a half in front of this one. And then I'm going to turn off first the half. So the 3 one is the purple line inside the red line. The red line's the original. Now what happened? Look what happens when I put a 3a factor in front of it. It got stretched thinner. See this black line, blue line? It got thinner. It got stretched up the vertical axis. This is called a vertical stretch. Now what happened when I put a value smaller than 1 in it? Well, it got fatter. It got fatter. I'm going to change the color here so that I have a different color. There we go. I'm going to make it blue. There we go. It got fatter. Now let's put a really small number in. Let's put 1 over 10 in there. Look how much fatter it got. So that's because all my y values got multiplied by a 10th and ended up happening a lot sooner along the x value. So it created what's called a vertical compression. It squished it all downwards. So I'm going to go back up to the original and put a 10 in front of it to see the difference. Here's one with a 10 in front of it. It's gotten stretched by a factor of 10. And this one's been compressed by a factor by 10. We can see that adding a factors is very obvious what happens. Adding a factors is very obvious what happens. And same, let's add a couple of, I'm going to take the parent parabola again, and I'm going to just add a, I'm going to add a c factor to it. I'm going to add a c factor to it. I'm going to just add something to the end. Let's say 5. I'm going to add 5 plus 5. My whole parabola should theoretically shift upwards 5. Yeah, it did. So you see it starts there now at 0, 5, and the rest is normal. It looks exactly like the other parabola. If anything, it looks like it joins it at one point, but you can see if we zoom in, it's always apart. But it's an exact shape, exact same shape as the original parabola. Everything is just moved up 5. Same if I subtract 5, the whole thing will shift 5 down below. My new vertex is 0, minus 5. So you can see that C translations are very easy to predict. They go up or down the y-axis. And you can see that a factors, when we multiply it, now I'm going to thin this one out. Look at that. I've added a 3a factor in front, and I've stretched it vertically by a factor of 3. It got very narrow. Its new vertex is lower, and it's stretched. You can see that any of these things here, any of these factors here affecting the a or the c are very easy to predict what happens to the y values. The tricky stuff is the k value. Let's get to some k value stuff. So we're going to get to the same parabola. And again, I'm going to just erase this original one. And I might have to use Desmos for this because the k values are interesting and annoying at the same time. Let's look at things that happen to the k value. So again, I'm going to skip the a value in front, and I'm going to skip the c value at the end. I'm going to look at stuff that happens in the brackets when it's attached to x and what happens to our x values. And oddly enough, your graphs are going to seem to stretch vertically again, but these are called horizontal stretches and compressions. Let's make it a 4x instead of 4x squared. So you might say to yourself, well, that's simply it's going to stretch x by 4, but actually it doesn't. It does not. The opposite thing happens here when it's a number in here. And to figure out what it happens is we simply take this 4. By the way, if any number is simply 4 over 1, that's the same as 4. And we simply flip it upside down to figure out what the actual thing happens. Well, this actually is 1/4. And that anything below 1 is called a compression. So this 4 in front of the x actually created a horizontal compression, which means it squished all the x values in this way. Now, you're going to say, well, that looks just like if I put this on the graph, here's the original, and now let me put a 4 inside the bracket. Boom, and then I'm going to say, I got 2 equal signs, that's why it's complaining. Boom, you're going to say, what? Wait a minute, that looks just like a vertical stretch. What are you talking about? Well, yeah, you're right, but actually what's happening here is the x values have squished this way, compressed this way, making it look like the y values stretched. But to calculate it, you actually have to look at your x values. And this is why we converted this 4 to a 1/4 to figure out what our plot points are. Now, you might say, why is this? I don't understand all that. Just trust that anytime we put a whole number here, the thing that happens is the opposite fraction. Any number below 1 is called a compression. Since we're dealing with the x value, it's called a horizontal compression. And it'll look a lot like a vertical stretch, it's true, but we're actually going to call it a horizontal compression, and I'll see why in a second. That is because you're going to get word puzzles that say horizontally compress this by 1/4, and that means you need to convert it to 4. Now you might say to me, well, I still don't get it, and that's okay. What if what if there's a fraction in front of the x in there instead? How do I figure that out? Well, again, you just flip this upside down. It's 4 over 1. We can skip the 1. It's simply a 4. That is above 1. So now we're talking about a stretch. Anything above 1 is a stretch, and it's a horizontal stretch. And guess what? A horizontal stretch is going to look a lot like what? A vertical compression. And when you think about it logically, it makes sense. If I stretch out my x values that way, that looks a lot like a vertical compression. But the reason we're doing it is to figure out what happens to the x values. That's why we distinguish it. So again, it's going to be a horizontal stretch, and we figure out by how much? By flipping that fraction. What good does this, why are we figuring out this number, you might ask? Well, that's because this number is what's going to affect all our x values. You might say if you took 1/4 there, you'd simply multiply all your x values by 1/4. Don't do that. That's wrong. We must first figure out this number by flipping this fraction upside down. Then, if this number is bigger than 1, it is a stretch. If this number was smaller than 1, so that again is if we had a 4 in front of the x, let's say, the conversion of that is 1 over 4, so that is smaller than 1, therefore that is a horizontal. Horizontal because we're dealing with x compression. Now this number that we figure out, and I'll go back to if it's 1/4, because that's easier for me to figure out my x values if I use it as an example. So let's say I got 1/4 x value, so I know I got to figure out what's going on. Okay, it's converted to a 4, so that's a horizontal stretch. And now I take that 4 and I multiply each of these x values. The y values in this case are not affected. That's why we distinguish k from a. A affects the y values, k affects the x values. So let's look. We first had to convert it to 4, and now we multiply each of these numbers by 4. Well, 3 times 4 becomes 12. 2 times 4 becomes 8. 1 times 4 becomes 4. 0 times 4 becomes 0. So we can see again, our vertex was not affected. Vertex are only affected by shifts along the horizon or the vertical. And then the same numbers happen on this side. This becomes minus 4. Now notice the minus still applies. It's minus 4 now. We multiply this by 4, it's minus 8. And this side becomes minus 12. And that's because now if I want to plot these points, and these are the only ones where I can plot on this graph, now I have to use minus 4, 1 is way out here, see? 0, 0 is the same. And then 4, 1, and the next number would be like 8, 4, which is way over here. Way over here. And now if I were to graph it, my vertex is a lot fatter. It experienced a horizontal stretch that way. And again, yeah, you'd say, well, it looks a lot like a vertical compression. Yeah, it does. Except to figure out my plot points, I'm dealing with the x values. And that's really where they make it complicated. These two things are slightly more complicated. It's why they put a minus here to tell you don't forget to do the opposite direction. And that's why the k thing, you've got to do a conversion to figure out what the actual compression or stretch is. So again, if you see y is equal and you see brackets 4x and then the square, the 4 is associated with the x. We know it's a k, and we have to convert it first to 1 over 4. 1 over 4 is smaller than 1, so we're talking about a horizontal compression. And now we multiply all our x values by 1 over 4. So let's go back and do that. Let's see. Hopefully it'll let me, that won't let me reverse the last stuff. So let's look at that. Let's look at y is equal to 2. So we're going to do y is equal to 2x squared. Well, you might say, oh, that 2, that's going to cause us... No, don't forget, we got to convert it. So what's the conversion of 2? We put it 1 over whatever that is, 2. So that's less than 1. We're going to experience a horizontal compression. All our x values are going to get multiplied by a half. So minus 3 times a half becomes minus 1.5. Minus 2 times a half becomes minus 1. Minus 1 times a half becomes minus 1.5. Oh, sorry, these are not minuses. These are all plus. My bad. Plus 3, it's because I had all the things there. Plus 3 multiplied becomes 1.5. Plus 2 becomes 1. Plus 1 multiplied by half becomes 0.5. Minus 1 times half becomes minus 0.5. Minus 2 times half becomes minus 1. Minus 3 by half becomes minus 1.5. And if I plot them, I'm going to discover that I have a compression like this. So if I plot, let's see, 1.5 instead of, so 0 comma 0 stays the same. My next number is 0.51. So it's right there. And my next number is 1, 4, which is way up there. And so I just mirrored on this side. And I can see my thing has gotten thinner again. And that's because I've had a horizontal compression. It's squished it this way, horizontal compression, by a factor of 1 over 2. Well, why don't I say horizontal compression of 2? This conversion is important. It's math speak. When they tell you your graph experiences a horizontal compression of 1/2, you will have to convert that to the 2 to figure out what the formula is. They're going to say it's a horizontal compression of 1/2. You have to convert it to figure out what the k value is. That's just math speak. Math speak, unfortunately, is something we have to deal with. But let's look at a couple graphs to figure this out. Again, our horizontal compressions are going to look a lot like our vertical stretches. So here I've applied a factor of 4, and you'll see all the x values got squished in by 1/4 of what they used to be. This used to be 2 comma 4. Now it's 1 comma 4. The x value, oh sorry, it used to be 2 comma 4. The x value became 0.5 comma 4. The x value got quartered. What if I put a 2 over here? So I'm over here now. What if I put a 2 in there? Well, all my x values should be halved. Sure enough, here's my x value right there of 2 comma 4, and it's now 1 comma 4. It got halved. My y stayed the same. My x's all got halved. Here I've got an x value of 2.5 comma 6, and it became 1.25 comma 6, half of it. So you can see it's easy to draw. My parabola is just halfway in between the line of symmetry and the old parabola. If it was a quarter, or if there was a 4 over here, the parabola is actually a quarter of the way from the line of symmetry and the original parabola. It's actually quite easy to draw. Let's look at some translations. So we're now going to deal with this d value. This d value. We're going to look at some translations. And I didn't quite do what I wanted to do, but that's okay. And we're going to look at some translations now. What happens if I have a formula that says y is equal to, open brackets, x plus 3 squared? Again, you might say, well, that's easy, Peter. I'm just going to do what I did with c. I'm just going to add 3 to all my x values, and hunky-dory. I get 6, I get 5, I get 4. I can easily figure out all my x values. No, sorry. When it's inside the bracket, these d's and these k's are slightly tricky. The d's are a little bit less tricky. You actually have to convert this sign to the opposite sign. That's why they have a stupid negative up here, to remind you to convert it to the opposite sign. All my x values will be converted by -3 shift. So if it's a normal parabola, all my parabolas get translated here by -3. So I take this -3 and I subtract all my x values by 3. So 3 minus 3 is 0. By the way, that's not the vertex. That's just a new line. 2 minus 3 is -1. 1 minus 3 is -2. 0 minus 3 is -3. That's my new vertex. -1 minus 3 is -4. -2 minus 3 is -5. -3 minus 3 is -6. And you'll say, are you sure? Are you sure? That seems wrong. So let's check it out. Here's the original parabola. And now I'm going to do the formula, and I'm going to add 3 within the x value. I'm going to add 3 within the x value, and I'm going to square it. And I'm going to now turn on that graph. And look at that. The whole thing shifted to the left by 3. Even though we had add 3 in the formula, it shifted it to the left. And this makes more sense if you actually plug it into the formula. So let's take our original plot point, and let's take 0, our original plot point of x, and plug it into this formula of x plus 3 squared. Well, if I take 0, my original vertex, and I add 3 to it, suddenly it's 3, and 3 squared is 9. And you're like, what? 3 squared is 9? Oh, that's because we're down here now. So the 0 value actually became a 3, and then got squared into 9. Okay? Now that might seem, you might say, oh, I'm confused by that. If you plot out this whole graph, let's do it. What will create a 0 here? What will create a 0? -3. Oh, so that's going to be our new vertex. Yeah, that's right. If you remember, the formula is you always opposite sign to find out the x value of the vertex, and whatever's over here is the y value of the vertex. In this case, we have nothing over here, so the y value is 0. Oh, so -3 is our new vertex. Yeah, that explains why the whole graph shifted to the 3. Yeah, but why then, when did we put in 0, did it become 9? That's because we're over here on this new graph. That's the plot point you figured out when you plugged in 0. What you need to do is figure out what value does x need to be to make this whole thing 0 to figure out the vertex. Well, it becomes -3. And that explains why a +3 here shifts the whole vertex to the left by -3. Now, unfortunately, there are some exceptions. Unfortunately, when we put a minus sign in front of this x, something weird happens, and we're going to get to that. But it's easier to understand that if I put a plus whatever, I'm going to put a +5 now, +6, the whole parabola shifted to the left of 6. Well, it makes sense because for this to be 0 in the bracket, my x value would have to be -6, so it shifts over. Now, obviously, if I put a -6 in this bracket, the whole thing's going to shift to the right by 6. Let's test it out. Yeah, whole thing shifted to the right by 6. What if I add at the end here a whatchamacallit value, a c value, I think it was. A c value to the y. Well, that should shift the whole thing. If I add +3, it's just going to shift the whole y values +3, because it behaves normally. Yeah, there it goes. It went up 3. It behaves normally on the y values. It behaves opposite in the x values. So that's the tricky part about the k value. Now, you're going to get some math problems where they say, you have a parabola. It is going to be compressed horizontally by a quarter. What is the formula? Well, first we flip that. They gave us the hint by saying horizontally, so we're talking x value. We're going to flip that. Flipping that gives us a 4, and that's going to go in front of our x value inside the brackets, squared. That's how we figure out this. So, compressed horizontally. What if they said compressed vertically? Well, compressed vertically gives us a hint that we don't change anything. They say compressed vertically by a factor of a quarter. We don't change it because they said vertically. So we simply keep it outside the bracket. 1/4 bracket x squared. That is a vertical. It affects the y. It just stays the same. So the hint is in the wording. If they say compressed horizontally, you'll know and they give you the number, you'll know you have to flip it to figure it out.